just a reminder, homework 4 is currently out, just due this Sunday. Next week is exam week. The final for the class will be a take-home final, which you should be able to kind of access through Gradescope. It will be available next week, starting Monday. You should be able to start it anytime between Monday and Thursday, return within 24 hours, or kind of submit within 24 hours. It will probably just appear as an assignment. I'll post an announcement about it. I mean, I expect the exam itself should take you no more than 3 to 4 hours, although you will have up to 24 hours once you start to submit it. Okay. Any questions about exam, homework, class, last lecture, anything other than anything before we continue the discussion for today? Okay. So, yeah, as in last couple of lectures, I want to continue this sort of applications of information theory in theoretical computer science. Today, in particular, I want to talk about a very nice sort of probability result called the Lovász Local Lemma, and an algorithmic version of it. And to be fair, the sort of it has an information theoretic intuition, but it's not like a very involved use of information theory, no more than saying that maybe sort of you cannot compress a string better than its entropy or something like that. So it's not using information theory in a very heavy way, but it has an information theoretic idea behind it, and it's kind of general. It's also used in other applications, and this in particular is a lemma which has many applications itself, so I wanted to at least discuss it. The basic setup is the following. We have some bad events, let's say B1 to B sub m on a probability space. Okay. And the subject of the lemma is, what is the probability that none of these bad events happen? Okay. The other kind of way of phrasing it sometimes in a more positive way is that we want to find some sort of perfect objects, and they can be bad in one way or the other way or so on. And a perfect object is one which is kind of not bad in any of these ways. And so and we'll see examples, but let's just first kind of do a little bit of a sanity check. So suppose all the events were independent, and let's say the probability of every event was some number between 0 and 1. What can we say about the probability that none of the bad events happen? So any guesses about what's the probability that this doesn't happen?
It's a product of the probability that each individual event that doesn't happen.
Yeah. So no, so I already wrote 1 minus. Okay. So in particular, if we have independence, then we can say that there is some chance that none of these events happen. And this is, let's say, positive if all probabilities are between 0 and 1. It might be very small. It might be a number exponentially small in m, but it's positive. So there is some sort of perfect object, or there is some non-zero chance that this will happen. Okay. Now, on the other extreme is just when we kind of don't know anything about these events, then, I mean, we can still do something, but it's not as strong a bound. So we can say that none of the events happen is less than equal to 1 minus the probability that any of the events happen. And sorry, this is equal to, and here we can bound it by the union bound and say that and this bound kind of only makes sense if the probability of each of these events is very, very small. We have used it. We use some sort of Chernoff bound to say that the probability of some bad event is exponentially small, and then we can take a union bound over a lot of them. And this is the usual argument we do. But there are often applications where we can't say something that strong, and we also don't have something as nice as independence. And Lovász local lemma is sort of a hybrid setting, which lets us say that if you don't have too strong a dependence, then you can say something which is kind of nice. So it's sort of in each of these cases, you would give up a little. And let's work towards the statement in a minute. But are these two cases okay? All right. So there are a few kind of ways of formalizing what it means that there is not sort of too strong a dependence. And one is to say that no event depends on kind of too many things, and its probability kind of based on the things it does depend on is not too high. And again, there are sort of different quantitative versions of this. But let's say we formulate some kind of a dependency graph. So let's say each vertex corresponds to one of the events. Okay. And we will form a graph, or sort of we will have an edge ij if I depends on j, and I'll clarify what it means. So and really, I mean, in sort of, we don't really define dependence, we define independence. And so actually it's the non-edges which are kind of more interesting. And what we mean to say is that for any conditioning beta, which is sort of any combination of on the non-edges, and we are thinking of it right now as a directed graph. So when I say ij, the edge is going from I to j. It's an ordered tuple. And all I'm saying, if there is not an edge, then you can be sure that there is no dependence, in the sense that you can have any combination of events among the j's that, let's say there is not an edge to 1, 2, and 3. So then we can say 1 happened, 2 did not happen, 3 happened, or whatever other kind of conditioning you want on these events. This will not affect the probability of di. Okay. But this is for non-edges, and there can be few edges. So there are few j's which are reserved, which you cannot condition and do this argument on, but the others you are free to do with whatever you want. And this is what I mean by saying that sort of j does not, like I does not depend on j, and then whatever is the rest we will kind of draw an edge to, and those are the things it depends. And one version of Lovász local lemma, which kind of goes like a hybrid between the union and independence bounds, is saying that suppose every event depends on only few things. So the out degree of a vertex I is less than equal to d, or the number of edges which have in the form I comma j is less than equal to d. So every event sort of depends on only few things or is kind of independent of all but D things. And the probabilities are not too high. So when we saw the completely arbitrary case, the union bound only made sense when the probabilities were about 1 over m on average. So they were super small. Now we want the probabilities to be about 1 over d or 1 over d plus 1 on average. And we are saying that the probability of every event, so this is the uniform version, and there is a non-uniform version when you don't want the same bound on everything. But uniform version says when the probabilities are all at most p, such that p is roughly 1 over d, or sort of a constant times this constant, like 1 over e kind of comes out of the proof, times 1 over d plus 1, then the probability that no bad event happens is positive. And I mean, yeah, actually the proof gives a bound which is about 1 minus 1 over d plus 1 to the n. So it gives some possibly very small probability, and we'll see them out in the more general case, and it will just imply this. But it's kind of interpolating between the two cases, that it depends on only D things, and the probability of each bad event is sort of roughly some constant times 1 over D. Then you can still make the same claim that no bad event happens with some positive probability. Is the statement clear? Let me state the more general version also. Okay. The general version is kind of saying that, okay, suppose you can give some bound on every, the probability of every bad event. So the bounds kind of are not just stated in terms of probabilities, but some sort of products of these things. So suppose there is one number pi for every bad event I, such that the probability of the bad event I is kind of upper bounded by pi times something which depends on its neighbors. Okay. So this is what we should think of as P in the previous, like this, the entire product on the right hand side. And here I'm not saying that the number of neighbors is small. It's just saying that you have these kind of parameters p sub j for every neighbor j, and the product of 1 minus p sub j times pi should upper bound the probability of bi. So if someone has a lot of neighbors, then its probability should be small. If someone has a larger probability, then it should not have too many neighbors. Okay. So it just it's kind of implied by these numbers p sub 1 to p sub m. These are just things that if you can find these kind of things, then you can prove a lower bound on the probability that no bad events happens. And I claim that this version actually implies the symmetric version. So let's say we want to prove the symmetric version, which means that we are given that the probability of each bi is less than equal to p, and the sort of the degree of bi is less than equal to d, and that p times d plus 1 is less than equal to 1 over e. Then let's find these numbers p1 to p sub m, which will imply the symmetric version using the general statement of the general version. And well, I guess I should take pi to be 1 over d plus 1. And so I know that for every event E, no, sorry, for every event BI, the probability of BI is less than equal to P, and I want to prove that it's less than equal to this product. So let's consider the product which I want to show this is what I want to show. And if I can show this, then I'm done, because then it satisfies the conditions of the general version. So the general version will imply that with some positive probability, no bad event happens. And I mean, yeah, this is just calculation based on parameters. So the RHS is equal to 1 over d plus 1 times 1 minus 1 over d plus 1 to the d. This is a known inequality that this quantity is greater than 1 over e. So the RHS is greater than 1 over d plus 1 times 1 over e, which is greater than equal to p by assumption. So it's a little bit of manipulation, but yeah, either of these versions can be useful. The symmetric version is the most commonly used in applications, although yeah, there might be cases where you really cannot bound the degree, but can say this kind of more fine-grained stuff. We'll not discuss the full proof of it because we'll see some sort of an algorithmic proof of some weaker version of this result. But let me mention the basic idea of the proof in case you want to try it out. You can read it in one of many places. I mean, in particular, the Allen and Spencer book on the probabilistic method will have a proof of it, or you can find it in many other places. If you want to try it out, it's not a difficult proof. Just uses induction to say that the probability that a bad event happen conditioned on some other bad events not happening is less than equal to pi, and sort of induct on the size of the condition. And then you can see that, I mean, and yeah, sort of in the conditioning, because BI kind of, there are some things which are neighbors, some which are not. So you want to basically split the conditioning into two parts, whether it's a conditioning on a neighbor or not. Okay, but you can also find this proof. So that's not a difficult proof, but the thing is the bound it gives on the right-hand side. So if you think of each of these PIs as some sort of constant between 0 and 1, and so the bound you're getting could be exponentially small in m. And so it's not guaranteeing that this event happens with high probability, and in fact, it might not. Yeah, I mean, you can think of even like trivial events like we saw that so if you have n bits, you're sampling each of them to be 1 or 0 independently, and so the graph is trivial, it's kind of the empty graph. And the bad event is that any of the bits is 0. What's the chance that no bit is 0? It happens with probability 1 over 2 to the n if you're sampling n random bits. But it's not a terribly high probability event. And so it's not sort of guaranteeing anything that this event is frequent in any way. Let's see an application of it, which is also kind of used as a proxy version of the lemma, which is the one we will actually discuss in terms of the algorithms. But I'll say a little more about sort of slightly more general setups. Okay, now let's think of K-SAT formula. So K-SAT, or sort of in general KCNF, is this kind of a formula where you are given an AND of clauses, let's say m clauses. Each clause is an OR of k literals, And a literal is just kind of either a variable or negation. So it's it can be either a variable or it's sorry, or the negation of some variable. So in every position you have either a variable written or its negation. And the probability space, let's say, all assignments to all variables, let's say sampled uniform. Okay. And n is the total number of variables. Okay. So we have m clauses, n variables, each clause has k variables. And if I define the ith bad event as the ith clause is not satisfied, then the event that sort of nothing bad happens is just saying all clauses are satisfied, or that the entire formula is satisfied because it's just the and of all the clauses. So there's another way of saying that there exists a satisfying assignment for this k-sat formula. And within a certain regime of parameters, Lovász local lemma can tell us that such a formula always has a satisfying assignment, or it implies something like this. And again, this is a generic way of sort of formulating many problems. P is the probability that a bad event happens, or it's an upper bound on the probability that a bad event happens. A bad event is ith clause is not satisfied. What's a good value of P, or what's a bound on P we might be able to use here? Any guesses, suggestions?
2 to the minus k.
Right. So we can actually compute the probability that a single bad event happens, and it's just 1 over 2 to the k, because you have an OR of k literals, and a bad event happens when all of the literals are false. So the first literal is false, it tells you what the first variable has to be equal to. The second literal is false, it tells you what the second variable has to be equal to, and so on. Yeah, I'm assuming that kind of no variable and its negation both appear in the same clause. So the clauses are non-trivial. If a variable and its negation appears and the clause is always satisfied, we can just throw it away. So each clause is, let's say, non-trivial. And it's a size exactly k. Okay. And the dependency graph here is that I will kind of join a clause Ci to a clause Cj if Ci and Cj share a variable. It might be negated in one, not negated in the other, that's fine, but there's some common way. And now it's a, so this is an undirected graph even. And if I look at Ci, and if I condition on something happening to clauses, none of which shares a variable with Ci, the probability of what happens to Ci remains unchanged, because the probability of whether Ci is satisfied or not only depends on the variables in the clause. And so so this dependency graph kind of captures what I want. If something is a non-edge, then Ci is independent of things it doesn't have an edge to. And So if I can say each clause shares variables with less than equal to d other clauses, then there exists assignment sort of assignment if p times p is kind of 1 over 2 to the k times the number of clauses is less than equal to 1 over e, or the number of clauses it shares a variable with is at most 2 to the k over e. This is an implication of the Lovász local lemma. And this is kind of also a more general setup which it captures, where what's happening here is that there is an underlying independent space which is these variables x1 to xn. And each of these clauses kind of depends on few of these xi's, and some other clause might depend on some other xi's, and they only interact if they share one of these independent things, if they share one of these independent variables. And a lot of applications are actually of this type, that the events are not independent, but they are defined on some sort of underlying space which consists of independent things, and the events themselves just depend on a small number of those underlying things. In this case, these are the variables x1 to xn. And the algorithm and the proof I'm going to present in general kind of works for this sort of setup, which captures a lot of the known applications. And then there are kind of later proofs which work in more generality, sort of the version I stated earlier, etc. Any questions about this KSAT application?
I have a question. So in the Lovász local lemma, I stated it's p times d plus 1 less than equal to 1 over e.
Yeah, you're right. I think I should also have, no, it should be d plus
1. Okay.
So d is less than equal to 2 to the k over e minus 1. Okay. Yeah, you're right. Okay, thanks. So as long as no clause shares variables with too many other clauses, it claims that there exists a satisfying assignment. And it's been an open question, or like, I mean, well, now it's kind of, well, for CNF, it's essentially resolved. But there's this kind of long-standing line of research about, we know there exists an assignment, can you find it? And more generally, as I said, this sort of question of finding perfect objects. So there are lots of things you want to avoid, you want to avoid violating the first clause or violating the second clause and so on. And you want to find this perfect object, which is an assignment which doesn't have any of these issues. It really satisfies all clauses. And these issues in this sense are kind of local. They don't always need to be, but they can be related more generally by the Lovász local lemma kind of probabilities. And the algorithmic question is, can you find such an object? And usually it's not always an sort of easy problem to find objects which occur with very small probability, at least algorithmically. I mean, if an assignment occurred with probability half, you could just sample sort of few random assignments, and the probability that you didn't find a good one would be small. So you just sort of take a guess at it. But if something happens with exponentially small probability, it's not so clear. And the history kind of is that, starting with the work of Beck, the results were of the form, instead of saying you can find an assignment when every clause shares a variable with at most kind of 2 to the k divided by some constant other clauses. The constant was in the exponent, so it's much smaller number. But if you kind of permit me that, then one can solve it for 2 to the k over 48, and Beck's result. Then Allen improved it to 2 to the k over 8. Srinivasan kind of had a result which sort of essentially implied 2 to the k over 4, and then there was and then kind of Moser improved it to 2 to the k over 2. The breakthrough result, which was I guess also the best paper in stock that year, was giving a result where some constant times 2 to the k. The constant was 1 over 32, and then this kind of -1 comes as before. This was later improved by Moser and Tardosh to the right number, 2 to the k over e. And I mean, yeah, there are also other things. The algorithm is very simple. It also has it's parallelizable. There are sort of parallel versions of this algorithm. There have been many applications since then in approximation. And in general, this kind of gives a useful technique for analyzing algorithms. And we'll see a proof of 2 to the k minus 3 minus 1. So instead of 32, we'll do 8, but not quite all the way down to e. And I'll sketch sort of what's the change between this proof and the really optimal bound. I should say that, I mean, can't expect much better than a constant times 2 to the k, because if you have all 2 to the k clauses on k variables with all kind of negation patterns on literals, this is an unsatisfiable formula. And each, because they're total, sort of in total 2 to the k clauses, every variable appears in at most 2 to the k clauses. So, so up to this sort of factor of e, which also happens in the sort of original Lovász local lemma, this bound is optimal. Okay. And we'll see a proof with 2 to the k over 8. And more than kind of the fact that this result is true, the algorithm is also extremely natural and simple. It's just start with a random assignment, capital X, where each variable is sampled independently and uniformly. So and if there is a clause CI which is violated by this current assignment, then we will call this routine to fix it. And throughout, they're kind of thinking that this assignment X is kind of written on some sort of global tape. So this recursive call will also have access to it. Will throughout use sort of keep accessing it. And if there are many clauses, we'll just fix the violated, which will just fix the lexicographically first one. So sort of pick one clause and try to fix it. And the interesting thing is, how do we try to fix it? So you have a clause, it has some k variables, and the assignment to those k variables is not so good right now. It's violating this particular clause. So you sample a new assignment for those k variables. Again, independently and uniformly. So each bit is chosen independently with sort of to be 0 or 1. So variables kind of true or false, 1 or 0. I'm hoping these are okay. I'm going to use them interchangeably. But you just resample the variables in that clause. And now, of course, you resampled it. So maybe sort of these k variables changed, and maybe some other clause which also involved one of these k variables might have been messed up. So you look at all the clauses which share, like C prime, which share a variable with C. If So I'm calling sort of the assignment I'm going to refer to this assignment as sort of X, or it's the current X. Maybe I can just say, let's call this X prime, and let's say variables which are violated by X prime. So X prime is the assignment after resampling. So X was a string of n bits. You rewrote the values for k of them based on what you sampled. And so this is X prime. And if there is a clause C prime which now got violated, which was in the neighborhood of C, we go fix that first. So in some sort of depth first search or depth first kind of routine, whenever you find something in the neighborhood of the current clause which gets violated by what you did, go fix that, then we will come back to what we were doing. Okay. And once we are done with all these fixes, we'll kind of go up in the recursion. Okay. Is the definition of the algorithm okay? Okay. I mean, the algorithm is very natural, although it's not clear it ever stops. It could just keep going in an infinite loop, trying to fix and sort of trying to chase its own tail and never really manage to fix. It sort of tries to fix one thing, something else gets problematic, tries to fix that, something else gets problematic. It's not clear when it ever stops. And the nice thing is that it can be analyzed in a relatively clean way. The first sort of observation is that if this subroutine fix, which we are looking at, if it ever stops, it's not clear if it will stop, but if it does, it's not going to increase the number of unsatisfied clauses. It doesn't change a clause from satisfied to unsatisfied. If it stops, I haven't made any claims about whether it stops. Because, I mean, yeah, sort of you can view the execution of this subroutine fix as kind of a recursion tree. You call fix on some clause, it resamples assignment for that clause, then looks at all other clauses which share variables with it. If one of them needs to be fixed, it kind of goes down that, and so on. It keeps doing this. Down sort of in the recursion tree, it might have to revisit an older clause, so that will just be a node. I will just kind of redraw that node at the bottom. So making just these recursive calls to clauses. And you can just sort of prove this claim essentially inductively or going up in the tree. So at the bottom level, like the call here terminated because we resampled this clause was satisfied. And so that's why we decided, and then all its neighbors were also satisfied. So they didn't get unsatisfied because of what we sampled here. That's why we decided to go up. And so if it terminated for the deepest node, it should be true that that node was satisfied and all its neighbors were satisfied. And by the way, yeah, so when I say a clause C prime which shares variables with C, this could be C itself. And so I will basically draw C as another node because it's doing another recursive call to C. It could be that I tried to satisfy C, I resampled the assignment, but this assignment I happened to sample the same thing, the same bad assignment again, and so wasn't very helpful. Okay, and again, if the call returned to this node, then every node it has visited so far is satisfied. That's why it returned to this node. Otherwise, it would still be stuck in the node which was not satisfied. So the recursion only returns after it satisfies all the nodes in the subtree. And my claim is that if the kind of recursive call to fix changed some clause from satisfied to unsatisfied, it must have visited it at some point. Because how did it get unsatisfied? One of its variables was resampled. When its variables were resampled, either that clause or something adjacent to it was a node in the tree. And when I have a node in the tree, I check all its neighbors. So the recursion tree, like the recursion returns to a node only when it satisfies the subtree. if any node is at any, if any clause is unsatisfied at any point, it must appear in the tree. By the sampling we did. If it was unsatisfied to begin with, I don't care. I'm just claiming that it was satisfied, but it became unsatisfied because of the sampling. It must appear in the tree. And when sort of call returns to a node V, subtree at V is satisfied. And this is just induction. So if the call terminates, it doesn't cause problems. The other way of saying is that if it does cause problem, it tries to fix them recursively. So it's not clear if it ever terminates, but if it does, I have something that it actually did not cause new problems. If there were old ones, that was fine. Okay, is that claim okay before we proceed? Okay, and now we know that kind of the recursive call doesn't cause problems, and it at least helps a little bit. So let's view this as a sort of two-level recursion. So this was the outer loop. We just sort of said, while there is an unsatisfied clause, fix it, and then fix itself had this sort of recursive calls which are drawn by circular nodes. And suppose we started with an assignment and C1 was not satisfied. We called fix on C1. This did not create any new problems, and it satisfied C1, right? Because we called fix on C1. So every time we run the outer loop, it satisfies one more clause, the one on which we called it. And it doesn't create any new problems. It doesn't unsatisfy any new clauses. It might change their assignments. Their assignments might not be what they started with, but it doesn't unsatisfy new clauses. So the outer loop has less than equal to m calls. The inner loop of the recursion, I have no idea. This might be, this might run for a long time, and I don't know how many calls it has. But the outer loop only has at most m calls, because every time we use the outer loop, one more clause gets satisfied, at least. Any questions before we proceed? This is just a long way of saying that what we need to analyze is the inner call or the recursive call to fix. Once the recursive call to fix returns, it doesn't create new problems. And if it was called from the outer loop, it at least gives me one more satisfied clause. So, but the inner calls might go on forever, and I need to say something about the do stop. Okay.
What is what would be incorrect if we try to say that when let's say we call fix on C1, right?
Yeah.
And when let's be assuming that it terminates, then each of the clause that you visited, all of them should be satisfied, right? Or is that not right?
Yeah, that's correct. Each of the clauses that it did visit should be satisfied. Yeah.
And you would visit every clause which, you know, it's like kind of like the connected component of that. When we look at
actually,
it
so it's not clear, because it might happen that I called it on C1. All the neighbors of C1 were already satisfied. Let's say C1 had two neighbors. Right? And so the call just returned, right? It just looked at C1. C1, because of the resampling, somehow got satisfied. The neighbors didn't get affected, say. Let's say I got lucky in the resampling. And there were like 20 other unsatisfied clauses in the neighborhood, but it never got to them. It's not going to go to the neighborhood until it finds, like, it only walks through unsatisfied clauses. It only visits. If this was the component of C1, right, it can happen that the boundary of C1 was satisfied, so it never actually got to this other node.
Right. So okay. So if it visits a clause, then that would be satisfied, but it might not visit everything in its component.
Yeah.
Yeah. Okay.
right? And when it visits, it sort of, so M is a crude bound. I can maybe do something more sophisticated, but it turns out to be not so necessary.
Maybe
but,
is it correct to say like something like M by D or something? Like we're assuming this D is this neighbor bound, right? Like, I mean, let's say if everyone is D.
Yeah, maybe. That sounds about right, because we are going to at least visit all its neighbors. So, so the clause we visit and all its neighbors are satisfied. And once they are satisfied, maybe. Okay. And now let's get to the part of saying that the recursive call does terminate at some point. I mean, first of all, we cannot hope to prove that it always terminates, because we might just get unlucky. We have one clause which is unsatisfied by the all zero assignment. We keep sampling, we keep getting all zero, all zero. If you've seen the Dilbert cartoon, there is a random number generator which keeps saying 99999. So, okay, so we could get that random number generator. But it has a nice caption like, "Are you sure this is random?" That's the trouble with randomness, you can never tell. So that's the trouble with randomness, that we might not be able to ever sort of satisfy even the current clause we are working with. Forget about the recursion. But in expectation, this won't happen, or the probability that we kind of keep going for too long will be not too large. So the expected running time will be small. And that's what we will prove. I mean, we're going to prove a stronger statement. The probability that the running time is large is very small, which implies the fact that the expected running time is small. And the way we will prove this is actually by saying that, let's look at the random strings, which are being used to resample these assignments. And we could get unlucky and we could have this string which is just zeros everywhere. But that string occurs with very small probability. And so in particular, the random strings which cause the algorithm for run for too long occur with small probability. And I'll sort of say this in one line as saying that bad randomness has a short description. This is how we will prove that there are not too many bad random strings. And I'll say later, but this is an idea which is used in a lot of proof, in kind of a lot of proofs in complexity, in combinatorics. Here, this is the first use I know in kind of analyzing the runtime of an algorithm. But this idea that bad randomness can be compressed or has a short description is a nice one and a fairly general one. Okay. So to formalize this, let's sort of say, let's look at the random tape of used by this algorithm for running up to time t. Okay. It might not have finished doing what it was doing at time t. It might still have some unsatisfied clauses. That's fine. We're just going to see what happens till time t, or we're just going to analyze the event that the algorithm runs at least for time t, or sort of so it uses all the randomness that we kept for it to use till time t. It might still need to go on. We'll just kind of terminate it and say, stop, let me analyze it. Okay. And E sub t is the event that the algorithm runs for time at least t. And I'm going to think of this random tape as having two parts. The first is kind of n bits, which was the initial random assignment. Let's call it x0 actually. And then we're going to think of it in terms of chunks of k bits. So every time an algorithm kind of needed to resample something, it needed to resample the variables in a fixed in a given clause. I don't know what clause, but it asks me for assignment to k variables. I read these k random bits and give it to the algorithm. Okay. So I have this random tape which has sort of k times t random bits for using in resampling. If the algorithm runs for time t, it will use all of them. And this kind of prefix of n bits, which it's going to sort of use at the beginning to generate its first assignment. Okay. That's the random tape. The event is just, it uses all of it. And my claim is that, okay, first of all, just a sanity check. I mean, yeah, as I said, it's not a fancy use of sort of information theory. You can write all of it in terms of counting, but well, since it's an information theory course, I'll use the information theory language. But what is the entropy of this state up to time t? It's not a difficult computation. It's
just t, right?
Well, it's okay. I'm thinking in terms of bits, so it's n plus kt. So every bit counts as one. So it's n plus k times t. Okay. And now let me count the entropy of the kind of bad randomness, or the entropy of R sub t, given that the algorithm kept going. And conditioning is kind of very simple here. This is the sort of space of all random strings. And conditioning just means that I kind of focus on this subset where ET is 1. So it's still uniform on this subset. It's just some other subset of random strings. And so I can say entropy conditioned on ET equals 1, or I can just say what is the number log of the number of bad random strings. Okay. And what I will prove is that the number of bad random strings is small, or the log of it is small. And I claim, okay, we have the uniform distribution on all random strings. We are saying that the number of bad random strings is small. Can you say what is the probability of the event t happening, or the algorithm running for time t? It's just the number of bad random strings divided by the total number of random strings, because I'm sampling uniformly, remember. Okay, yeah, when t is smaller than m log m, this bound is kind of bigger than 1, so it's a nonsensical bound on a probability. But when t becomes large, this bound will start becoming interesting. This is also what we saw, for example, in sparse mean estimation, that we want to talk of expectation of a random variable. We try to understand what's the probability that, okay, actually I don't need this n here. I already have this m log m. I can cross this out. And what we just saw was that if I think of the time, the running time as a random variable, then the probability that the time is larger than m log m plus s, or the probability that this sort of capital S, which is the excess running time, is larger than some value small little s, is at most 2 to the minus s. Okay. Again, I don't need this, but it's kind of anyway included in the order m log m term. Sort of it's bigger than order n anyway. So the number of runs is basically m log m plus whatever is the expectation of this excess random variable capital S. And as we saw there, this can be written as a summation of the tail, which is less than equal to so the excess running time is small in expectation. So the expected running time is basically order m log m. Doesn't take much longer than that. And I mean, we also have the fact that the probability it takes longer is small, in case you want to use that instead of the expected running time. But basically m log m. You can actually even be more clever and get order m. Sort of the m log m bound I'm going to give is a bit lossy, but that's fine. Okay, so if I can prove that the kind of entropy of the set of bad random strings is small, then we are done. Is that okay before we proceed? And this is a kind of nice observation that this kind of random string is, you can basically recover the random string based on what the algorithm did. So the random string r sub t, if it ran for time t, then we are going to look at sort of what happened over time t. And we can recover the random string based on what was the final assignment the algorithm was working with after time t. Let's call it x sub t. And this execution log, which is which I will call log sub t with a capital L. Hopefully, it won't confuse with the logarithm function. Okay. So my claim is that whatever I will get will actually be a function of x sub t and log sub t, this kind of random string. So in particular, its entropy is upper bounded by the sum of those two entropies. And let's just sort of see one step of this. It's just again a recursive procedure, so like a relatively simple one. And by log, I will take it to mean just kind of the names of all the clauses which the algorithm visited. So I don't care about other steps in its execution. The only thing I care about it was when fix was called on some clause, and that's the number of calls I'm going to bound, and the rest of the running time doesn't matter so much. We basically want to understand. This is fix used throughout the algorithm, outer, inner loop, everywhere. Okay, let's say this is just the total number of uses of fix. If I tell you that at time t, fix was called on clause c sub t, and I sampled this assignment which I got, which was x sub t, I claim I can recover the previous assignment, x sub t minus 1. So I can sort of go back in terms of randomness. This also tells me, okay, first of all, it's clear that the last part of the random tape is just the assignments of this, are just the variables for this clause, right? Because I told you that at time t, clause t was resampled. Okay. And I tell you what's the final assignment we got after that. So of course you can read it and tell me what were the last t bits on the random tape. I claim that you can also tell me what the second last assignment was, and then we will kind of keep running it back. Any guesses on what the second last assignment was? It only changed in these positions that we already know, because we only resampled these variables. But we also know what the old values were here.
Is it the unique assignment that made the clause unsatisfied?
Exactly. So for every clause, there is a unique assignment that falsifies it. Falsifying CD. So, and then we can just keep going back. So given the final assignment and the final clause, I told you what were the last t bits of the random tape and what the previous assignment was. Now, the execution log is all the clauses. So you, of course, know the second last clause which was sampled. And now you also know the second last assignment. So now you know what were the kind of second last portion of k bits on the random tape and what was the sort of third last assignment, or xt minus 2. Keep running it back. So if I tell you all the clauses that were visited in order, and if I tell you what the final assignment was, you can run this process backward to recover the initial assignment and all the bits on the random tape, which was the initial randomness. And we are using this, assuming that this randomness was such that it led you to run 40 times. So this sort of every kind of bad randomness can be recovered this way, running this process back 40 steps. Okay, so now the final assignment itself was has entropy at most n, and we were planning to prove a bound of the form n plus order m log m plus k minus 1 times t. So the n is just corresponding to the final assignment. That's easy. And now I want to prove that the log, or the kind of run in the execution transcript of the algorithm, has entropy at most order m log m plus k minus 1 times t. So I can write down the kind of log of the algorithm in well, yeah, it doesn't have too high entropy. The way I will prove it is by saying that I can actually compress it into a small number of bits, and that's why it won't have too much entropy. I can always describe it using a small number of bits, and then the number of bits will be whatever is on the right hand side. Any questions about the claim? Okay, and the idea is very simple. So at every point, we kind of try and visit a new clause. And all I need to write down is sort of tell you what is the next clause I'm visiting. Basically, there's a little more I have to kind of tell you when I return from a previous call, etc. Okay. But think of it like writing a list program that you kind of open a bracket, you write down the new clause you are visiting, and once you come back on that tree, you kind of write down a closed bracket. Okay. So you open a bracket, write down the next clause, and then this might kind of open more brackets, or sort of this call might recurse, so you might kind of go into some sort of loop. But when you come back, you will close the bracket. So this is the way we will write the transcript or the recursion. Okay. And the question is, how much do I need to write down for the next clause? Every time I write next clause, for open bracket and close bracket, I'll just use 1 and 0. So I will use 1 to say I'm opening a bracket, 0 to say that I'm closing a bracket. And in between, I will use strings of fixed length, so it will not be confusing. I sort of I will have some sort of fixed length string here, which will tell me what's happening. And now, if I'm in the inner loop, if I'm kind of doing one of these calls, then I'm claiming that for the next clause, I can write down a string of at most k minus 3 bits and tell you what's the next clause. Because you know where I am currently. I'm assuming that the transcript so far has been recorded. You know where I am. I'm going to visit one of its neighbors. I just need to tell you which neighbor. Each clause has at most 2 to the k minus 3 neighbors by assumption. Shares variable. So I just need to write down the index of the neighbor. And we can just assume that all clauses kind of globally are numbered from 1 to m. So when I say index, I'm just going to tell you, yeah, the 10th one of my neighbors. And you know what ordering I have in mind. It's the global ordering of 1 to m. In that ordering, I'm just talking about my 10th neighbor. So you can write down a k minus 3 bit string. And that should be enough. You know what clause I am at. So even if I have less than 2 to the k minus 3 neighbors, you already know that. So I will just use some dummy indices if needed. All right. Now for the outer call, I will need to use a larger bit string because I have to sort of clearly indicate it's an outer call. But this is only going to happen m times, so I don't really care. So I can write down sort of and I can put stars on both sides if I want to, so that this is a longer length string, but you know sort of that it's going to be a longer length string. So I'm going to just introduce this extra symbol and write sort of this index between stars. So all the inner clause strings will be of length at most k minus 3. And there will be kind of 1 bit for opening a bracket, 1 bit for closing a bracket. So I pay k minus 1 bits for every inner call. Outer call, I pay some order log m bits. I don't really care. I'm just going to pay this m times. So I can write down the transcript using order m log m plus k minus 1 times t bits at most. And so the entropy is at most this much. Any questions? Okay, yeah, I mean, you can also think of it as some sort of process. Basically, every time you resample a clause, you use up k bits of randomness. But when I tell you what neighbor I'm talking about, I only use k minus 3 bits of randomness. Even with this open and close bracket, it's k minus 1 bits of randomness. So at some point, kind of the amount of randomness I've used up will be more than what I'm leaking in this way, and this will be a compression. And that's basically it. I mean, that proves the theorem or the version we claimed, that you can write this k minus 1 times t. The optimal bound basically says that instead of doing this sort of decoding at encoding that at every vertex I'm telling you what is the neighbor I'm talking about, it's 1 of k minus 2 to the k minus 3 choices. You just encode the whole tree and you just count what is the total number of trees which are possible, which have these m top nodes, and every other node has degree at most d. And it's just a sort of counting argument that the number of such trees can be bounded in this way. It's not too hard an argument. I can show it later if you like. But it's and that basically gives the optimal bound. So it is just a slightly more clever argument. Instead of saying that every point I just encode my neighbor, I encode the whole tree. This is, and then that's the whole proof. We recover it basically with 2 to the k divided by 8 instead of 2 to the k divided by e. This argument has kind of many applications to algorithmic and approximation algorithms in particular. And there is a nice sort of follow-up paper of Eupler, Bernard Eupler, Barna Saha, and Arvind Srinivasan, which gives this. There is the Moser and Tardosh paper from 2010, which I mentioned, kind of proves optimal kind of statements for Lovász local lemma for all things which are of this form, that there is some underlying independent space and every event is kind of depending on few of these underlying variables, like KSAT. There is a generalization to kind of the more sort of standard setting of Lovász local lemma for events using Harvey and Nick Harvey and Jan Vondrak. It's not quite in the resampling, or like it is resampling, but it's not quite as entropy compression, because somehow so far the entropy compression arguments don't work well when the kind of you don't have uniform distribution on some underlying space. And when you have events in general, but not that there is some sort of underlying product space, don't sort of have this property, but there are other ways of generalizing the arguments. There are kind of two interpretations of the Moser-Tardosh proof, and both of them, in fact, there are other interpretations and extensions in this very nice follow-up set of works by Kleoptas, Iliopoulos, and Sinclair. And in particular, Iliopoulos, he kind of graduated recently. His thesis is actually a nice place to read about some of these developments if you're interested. Let me remark that this argument that bad randomness has short description appears in many contexts, kind of both before and after this particular application. The sort of novelty here is to use this idea to analyze the running of an algorithm, and in particular backtracking algorithm. And it's been since used in many kind of analyses of block backtracking algorithms, not necessarily by these authors, but many sort of other authors. One of the earlier instances I know of this idea is Razborov's proof of what's called the switching lemma by Johann Hastad. switching lemma kind of says that if you have a circuit, or in particular, let's say a DNF formula, which is instead of being an AND of ORs, it's an OR of ANDs. If you set the variables in it randomly, then it becomes very simple. It can be computed by a very, very simple circuit if you set a lot of variables randomly. The formula on the remaining variables has a very, very simple structure. And in particular, it's a low depth decision tree, if you know what that is, but otherwise it's just some simple structure. And the proof is that the probability that it doesn't simplify is just another way of saying that you have bad randomness. And Rasborov's proof kind of says that when you have a formula which doesn't simplify, then the random values that you chose for the variables to set can be encoded in some short way. And so it happens with low probability. So also used in a kind of follow-up and very recent work, also stock best paper in 2020, which was a proof of kind of near optimal bound for the sunflower lemma by Ryan Alvarez, Shachar Lovett, Kevin Wu, and Yipeng Zhang. Okay, I forget his first name. Sorry. It's and this was kind of more explicitly stated in this paper of Rao, which was sort of simplifying the proof also to some extent. Yeah, I mean, there's also a later kind of blog post by Terry Tao where he kind of reinterprets this sunflower lemma proof entirely in terms of entropy without using sort of any encoding at all. But yeah, it depends. Both encoding and the entropy argument are a little more involved here. The Lovász local lemma is the kind of cleanest instance of this idea that I know of. But yeah, just to say that this technique of compressing bad randomness is a general proof technique. And first is kind of circuit complexity or proof complexity, and the next is an algorithm and approximation algorithms, and the last one is kind of closer to combinatorics. It appears in many areas. Okay, let me stop here for today. And yeah, next lecture, I'll talk about another kind of recent result from, I guess, Stock 2016, which is also the best paper. I guess so. If you want a Stock best paper, you know what technique to use. You find your problem then. But it's a kind of nice information theoretic proof of the fact that Reed-Muller codes achieve capacity for certain channels. So it kind of has both information and coding theory in it. And it's again a nice argument which came out of a combination of ideas which were more traditional in TCS and analysis of Boolean functions versus ideas which were more common in information theory literature. And it just kind of is a nice combination of the two. Okay, that will be the last lecture. A reminder again, the final is next week. You should be able to take it start it any day between Monday and Thursday, return it in 24 hours. I'll post an announcement with more details on the format. Should be available through Gradescope. I'll just double check this Monday to Thursday thing. Make sure there are no kind of requirements from the university to declare grades earlier, but otherwise this is the plan on my part. And yeah, the homework, the fourth homework is due on Sunday night. Any questions, comments?